Our last video for Chapter 3, Section 1 talks about the different connections that we can find between graphs of the original functions and graphs of the derivatives of those functions. This is something that's going to be a little bit difficult in this lesson probably because it's so new, but by the time we get through the end of Chapter 3 this will make perfect sense to you guys. Okay, so what you're seeing here are three functions, and we're going to graph the derivative of that function over top of each one. So keep in mind that the derivative is simply the slope of the tangent line of that function. So if we look at the first one, the original function is just a straight line, and basically the slope of the tangent line is going to be the same no matter where we are, because the slope of this line is always the same. And so this would be a lot easier if the grid that is supposed to be on here would actually show up. But to find the graph, or to find the slope of a line, we simply measure the rise over the run. And so for this example we might say that the rise would be 3 compared to 1. So this entire line here has a slope of 3. So to graph the derivative then, if this one right here is function f, maybe in blue I'll do all of the derivatives. The derivative at any point along here is always going to be at a height of 3. That would be f prime. What does that tell us? It says that if I'm looking at the function here, what's the slope right there? I just look at the derivative at the same point. Oh, the slope is 3. Right here, what's the slope? Oh, the slope is 3. What is the slope of the tangent line right there? Oh, the slope is 3. So the y values of the derivative are telling you the slopes for the same x value of the original function. Okay, let's look at another example here. Let's see if I can slide everything over. Perfect. So again, this would be a lot easier if you could see the grid, but what you are hopefully noticing is that we have now 4 line segments. Here it's a negative slope, a slightly steeper negative slope, a slope of 0, and then a positive slope. So if I were to, again, think of rise over run, I might think of this as being down 1 and over 1. And I do the same thing for the other 3 sections. This tells me that the slope of the first section here is always going to be at negative 1. So I would go down to what I think negative 1 would be at, and that's going to be how I start the graph of my derivative. Maybe the slope of my next section right here is going to be a little bit steeper, negative 1.5. So there I would go down half a step and draw my derivative all the way out there. We probably, for this, would have to say, and we'll get more into this more in section 2, we'd be putting open circles at the end of all these, but don't worry about that so much right now. Our next chunk here, the slope of that entire chunk is always 0. So we can make that a little darker so you guys can see that better. And then the slope of our last chunk, now it's a positive slope, maybe that's a slope of positive 1, we'll say. And so for that chunk I'd go something like that. Again, open circles here and here and here. Won't worry about endpoints, we could probably fill in actually, but all these are minor details for this lesson. So what is this telling us? Again, it tells us that if I'm looking at any part of the original function and I want to know the slope at this particular point, I just go and look at the same x value as the point I'm interested in. Oh, it's got a slope of negative 1. Maybe I'm interested in this x, or this point right here. Okay, so with this x value, just go straight down to the derivative. Oh, a slope of negative 1.5. I can do that throughout. It's just telling me what is the slope of a tangent line at that particular point. Okay, third example is going to be a little bit more challenging because now you notice we have some curves. So this one looks like an upside down parabola. And again, as we work through this chapter, you're going to figure out that this is a lot easier than this particular example will be, just because it's so new. But because it's curved, I'm just going to look at maybe a few set points. I'm going to look at that point because it's right way at the top. I'll look at this point and this point, maybe something kind of in between. Okay, so as we're mapping our derivative, right away, the slope of the tangent line here, this would have a slope of 0. So I know that it's got to go through a y value of 0 right there. I'm just going to go a little bit to the left. This has a positive slope for the tangent line. This also has a positive slope, but it's going to be a larger number because it's a little bit steeper. And so that tells me that maybe at this point, maybe it's going to go, maybe it's got a slope of, maybe it's a slope of 1 there. And over at the next one, maybe it's a slope of 2. So I'll just kind of go up a little bit higher there. And then if I look at the right side, this is going to have a negative slope going downhill from left to right. This will have a steeper slope. And so again, this one might have a slope of -1 right there. Maybe this one has a slope of -2. We'll just kind of connect them. We're just kind of guessing here. And maybe that is the slope of the derivative. So this was f prime, and this one is function f. What you will find as a pattern here is that the derivatives, if we're looking at polynomials, will get 1 degree smaller each time. So if this was a degree of 2, a parabola, something that has x squared, this one will have a degree of just x to the first, or a line. You'll see that pattern going on for quite a while. Just want to make one quick change here as we go over here. I did not label things. I want to make sure this is connected in your notes. That's the graph of f, and in blue that is f prime. Okay, moving on to our last slide of this entire section here. Okay. So in this one, now we're looking at it opposite. Now we're looking at graphs of the derivative, and we're going to try and graph the original function. And one thing they do tell us is that the original function for both of these has to go through the point 0, 2. It's saying that when I plug in a x value of 0, I get a y value of 2. We're going to talk a little bit in class about why that's important, so maybe this question right there we'll talk about in class. Okay, let's look at the first one here. Zoom in a little bit. And again, this would be a lot easier to figure out if our grid was kind of set up, but I do know that it's got to go through. Here, we're going to color code this again. This is going to be f prime, so now black is f prime and blue will be function f. I know it's got to go through 0, 2. Okay, now what does this mean? This is telling me that my slope for this entire section is always going to be a slope. We'll just say that's -1. So I'm going to have a line with a slope of -1 going through all the way to here. Something like that. Okay, so it's telling me the slope, and that fixed point there is kind of important so I know where it goes through. And then maybe the next section here, that might be telling me that the slope for that entire part, that's got maybe a y value of 2. So my slope from here is going to be a little steeper. It's going to have a slope of 2 going all the way out. Okay, so this would be the original function. We're working backwards now. I don't know if they're telling us that the function was continuous or not. I'm assuming that it probably was supposed to be, so that's why I can kind of say it's connected right there. That might also be something that I talk about in class, or you can ask a question about if you want to. Okay, last example, last sketch here, a little bit more challenging. Again, because there are some curves going on here. So again, this is going to be f prime, and in blue will be function f. So I know it's got to go through 0, 2, remember, so I'll put a little point right there. This one's going to be a little bit more complicated. What I do know is that right here, this is the highest value for the derivative. So that means that's where it's got the largest slope. It's going to be the steepest right in here, and it's going to kind of gradually turn. It's going to decrease as we go through. And then at these 2 points, at those 2 x values, that's where I have a slope of 0. So here, these are all positive values. I'm always going uphill throughout, and when I get to right about here, it's going to have to make some sort of a turn, have a slope of 0, and then from the rest of it, it's got negative slope. It's going to be going downhill. Same thing right here. It has been going uphill. When we get to this x value, wherever it is at that x value, it's going to have a slope of 0, and then start going up like that, because as we go here, it's got to have negative slopes all the way through this x value, because they're all negative values there. So this is very much an estimate. I'm not saying that yours would look exactly the same. We'll get better at getting exact values for this, but like I said, maybe this is going to be a kind of a big point right there, and maybe here this will be kind of a big point right there. And so as an estimate, I might have an overall function that's going to do something like this, and just kind of go down, maybe here, or something like that. Oops, except my min should really be a little bit further that way, just kind of make that change. But that's going to be basically what it's going to look like, something like that. So remember, this is a parabola, degree of 2, and it looks like our original function ended up having, this looks like a cubic to me, a degree of 3, and as we go from the original to the derivative, it generally will lose a degree. So that seems to be true as well. Jot down any questions you might have over these last couple examples here, and be ready to ask some good questions in class.